Welcome back to ECE 320A. If you're just arriving, you missed the fashion show that we just held. But for those of you that were here, thank you for your bids and your attention. And we will get started. We have quite a bit happening in the next week. A week from today is exam number 3, and that will cover material on homeworks 6, 7, and 8. I've forgotten what was on 6. 7 was convolution, so we'll have to go back and remember what 6 was. But we will have a review session. I don't yet know where, but it should be on campus somewhere. So hopefully on Tuesday's lecture, we will be able to tell you, confirm when that or where that's going to be. I believe it will be at 6 p.m. on Tuesday the 19th. Your homework number 8 is due on that day, and most of the material that you will need for homework 8 we have covered. We'll cover it a little bit more thoroughly today, and we'll try to get into Bode Plots and what that means, and that will hopefully give you even more background or familiarity with these concepts that we'll be talking about in terms of break frequencies or cutoff frequency or break point, etc. That's what I want to do today, is go through or continue to work through these graphical evaluations of a transfer function at a single frequency, omega naught. If we did that for many different frequencies as we're walking up the imaginary axis, we would then generate Bode plots. If we would keep track of the magnitude in dB and the angle as a function of frequency. That's really what Bode plots are doing. They are simply stepping through this process of determining how our system responds at particular frequencies. That's what h of j omega naught does. That basically says, given this system, which in our case a lot of times is a circuit, you could think of it as a filter, given this filter, how is it going to behave at a particular frequency? And we're calling that frequency omega naught. Last time we had this transfer function, or this system, it has 2 complex poles, it has 1 real zero, and it has some DC gain associated with it. And what we want to be able to do is figure out how to determine what that system will do at a specific frequency. If we start shaking a system at a frequency, how is that system going to respond at that particular frequency, let's say omega naught? I've written then in the second equation on the screen the denominator factored into its complex poles, or its complex pole factors. We have poles at minus 3,000 plus and minus j 4,000, and I'm trying to emphasize which of those factors are in the second quadrant and which one is in the third quadrant. That's important for understanding distances and angles that occur when we're evaluating h of j omega naught graphically. So that's what we want to do. We want to step through this a little bit more carefully. I think last time we did quickly go through this particular example. We may have done it at a frequency of omega naught equal to 5,000. Let's look at it for a different frequency. Now the frequency is where I've indicated this triangle. It's now at 2,000 radians per second. It's J2 times 10 to the third. And we have our 3 singularities. We have a pole in the second quadrant. We have a second pole, which is the conjugate of the first pole, in the third quadrant. And we have our finite zero that's real, and that's on the real axis at minus 5,000. Is it clear what I'm trying to indicate with respect to the information associated with each of these factors? If we go back to our transfer function, I'm going to be referring to different pieces of this transfer function. This I would say is my zero factor. This would be my, let's say, the pole factor associated with the pole in the second quadrant. And I'll refer to those as factors. And each of those factors produces a magnitude or a length or a distance from that particular singularity to the frequency in question, and it also represents a direction or an angle from that singularity to that particular frequency. And if you draw these diagrams to scale, you can get a visual perspective in terms of the angles and the lengths and how they contribute to the magnitude and angle of the overall transfer function h of j omega naught. But we will now look at these different pieces individually. We can compute L sub z. And that's just, and all of these lengths are just the Pythagorean theorem. It's just the hypotenuse of a right triangle, where you have the real part representing the horizontal distance and the imaginary part representing the vertical distance. That's just the two sides of a right triangle, and we can use the angle basically as the inverse tangent of the appropriate opposite side over the adjacent that we're looking for if we use the inverse tangent. Let's look at the case where we want to evaluate h of j 2000. Now this is different from, let's say, Tuesday's lecture. We've now replaced s everywhere with j omega, which now says that we are walking up the imaginary axis in this expression for h of s. And I think last time this was our imaginary axis. Is that true? I don't know. They were giving out free pizza on the mall, so I said I would get you guys started and then I would leave and eat. How's that? Oh, that didn't go over very well, did it? Whoops, I'm going to fall down. Then you'll have a laugh. Huh. Don't laugh. Well, you could if you wanted. That would be silly if I fell. Teach me right, from walking up and down. So here we have too many cords and wires. This is what we want to do. We want to calculate L sub z. That's just, again, the Pythagorean theorem. L sub p1 and L sub p2 for the zero factor, the pole factor, and the two different pole factors. If we look at the zero factor in particular, if we keep that multiplication factor of 10 to the, or of 1,000 there in mind, what's L sub z? What's the length from the zero to the point on the imaginary axis represented by a frequency of 2,000 radians per second? So it's 2,000 squared plus 5,000 squared, isn't it? And I'm going to simply keep that scaling factor to the right so that my computation of the square root doesn't get so big in terms of numbers. But now I have this is equal to the square root of 29 times 1,000. And the square root of 29 is a little bigger than 5, square root of 25, and it's a little smaller than the square root of 36. So I'm somewhere between 5 and 6 in terms of distance scaled by 1,000. And if you actually compute that, you end up being at 5.385 times 1,000. That's L sub z. Is it clear where that's coming from? You could say that you are now at this particular zero location. If you walk over 5,000 and then up j 2,000, that's exactly what that particular factor is giving you. Yes? Where did the 2,000 come from? From thin air. So the J2000 right now, you don't know where that came from. Later I'm going to say, suppose we have an input at a frequency of 2,000 radians per second. I simply selected that 2,000 as a value that illustrated that the angle associated with that upper pole can be negative, its contribution. Each of these singularities presents itself with different magnitude contributions and angle contributions. And I picked something that was less than J4000 so that the angle of that upper pole would be negative. And you need to keep track of the signs of those angles. That's the reason I picked 2000. It hasn't there was no justification for that on the notes or this presentation so far. Does that help clear things up? So 2000 I simply grabbed out of thin air. Actually, I think I picked it up somewhere on the stairs. And it was just a number. There was no dollar sign, so everybody's starting to rush over to the stairs, but there's no dollars associated with that 2000. For those of you that are only watching or listening to these videos, you're really missing out. All right. That's the length due to the distance from the 0 to J2000. And now I hope it's clear, if you picked a different frequency of interest, that triangle is just going to be at the appropriate location on the imaginary axis. The angle of theta sub z is now the inverse tangent of, so it's opposite over adjacent, isn't it, is the tangent. So this one is now 2000 over 5,000, and all of those zeros conveniently cancel, and we really are just left with the inverse tangent of 0.4, and you need to make sure your calculator is giving you the right units, or you're using the units that you think you are, but that's now 21.8 degrees, and again, if you've drawn these accurately, you can see that that angle should be less than 45 degrees. In order for it to be 45 degrees, we would have been looking at a J5000 for our evaluation point. What about are there questions on the contribution of that zero factor? That's your length and angle of the zero in that transfer function. The upper pole factor is now this J omega naught, which we conveniently picked to be J2000 plus 3000 minus J4000. That's the factor of the pole in the second quadrant. If we sketch that, our pole is sitting right there, and you can see that, in fact, if we, and we want to get to this point right there. If we now go down minus 4,000 from our pole, we would be right there. If we go to the right 3,000, which picks up that piece, we're right there. And now if we go up 2,000, we are right at that triangle. So now we're taking a walk on horizontal and vertical directions, but in fact, we are interested in getting from the pole to that location, which is that distance. And this is now our L sub P sub 1. And the angle is always measured relative to this positive horizontal line, and our angle for that pole factor we will label as theta sub P sub 1. If we combine all of these, we now have 3000 minus J2000, and we're really just interested in the length and the angle of that complex number. And that will give us that L sub P1 and this angle theta P1, which is the contribution due to that single pole in the second quadrant. Or L sub P1 is now this square root of 2 squared plus 3 squared times 1,000, or that's now the square root of 13. And L sub P sub 1 now becomes this 3.606 times 1,000. How did I get 2 decimal points? I think that's just a shadow, I hope. Questions on that? So that's not a new notation. That's not March 6, 2006 times 1,000. Oh, it is appearing on the screen, though, isn't it? But did anybody see what happened on our special day, Tuesday? All these people started getting married. The next day in the paper, 11, 12, 13. You know, I made sort of a big deal about that. There were many, many couples that became blissfully wed on 11, 12, 13. I don't know where that, oh, that came from this. 3606. But I'm hoping that second decimal point goes away as soon as I start writing again. Huh. I'll force it to go away. Okay, it was actually there. It wasn't virtual. I must have touched the screen. Questions on 3.06 or 3,600. That's the contribution of that upper pole to that frequency of 2,000. Theta P1 so now we need to keep track of that direction. It's actually minus 2,000 down. It's down 2,000 or a minus 2,000 over 3,000 over, and this now ends up being minus 33.69 degrees. And if we look at the lower pole factor, which is J2000 plus 3,000 plus J4000, we now have this particular location to concern ourselves with relative to that desired location of J2000. So if we go over 3,000, up J4000, and then up J2000, we get to that location, and that's now this distance, L sub P2, at an angle of theta sub P2, where L sub P2 is now this square root of 3 squared plus 6 squared, or the square root of 45, times 1,000, which is not quite 7. It ends up being, did I write it? 6.708. And the angle, theta sub P sub 2, is the inverse tangent of 6 over 3, already canceling all the 3 zeros in the numerator and denominator. And this now ends up giving us an angle of 63.43 degrees. We now have all the pieces that we can use to build up the value of our transfer function at this frequency of 2,000. We now have 1,000. We have to keep track of the scaling amount that was not included in any of our pole zero factors. LZ at an angle of theta z over LP1 at theta P1, LP2 at theta P2, or this is now some magnitude at some angle, we have all of the angles in the numerator and we subtract all of the angles in the denominator. If we perform the computation, we end up with the magnitude of our transfer function at that particular frequency is 0.223, and the angle is the 21.8 degrees minus a minus 33.69 plus the 63 degrees, or that ends up being a little bit less than 0. So that now, in anticipation of somebody saying, what if you're given an input x of t, which is 2 times the cosine of 2000t minus 10 degrees, what's the sinusoidal steady state of the output? And when will we reach the sinusoidal steady state output? 5 tau. And what is our tau in this case? I guess I could show it from any of those diagrams, but here is all of our poles and zeros. Could you find a tau if I gave you this picture? Pardon? So now what influences our tau? Poles, zeros, none of the above? It's not our zeros, is it? It's our poles. Our poles are what we have in the denominator when we do our partial fraction expansion. So if you sort of get lost, just say, wait a minute, I can think of this as a partial fraction expansion. And then I have all of these pole factors giving me contributions to my system response. And the ones that I'm interested in are those that are associated with my transfer function h of s. This one had poles with real parts of minus 3,000. So now we have an e to the minus 3,000t with some cosines and sines. And what's the frequency of those cosines and sines? 4,000, isn't it? But that's not influencing our tau. Our tau is basically how far into the left half plane do we have to go before we reach our first pole. That's our slowest pole. In this case, it's e to the minus 3,000t. That's pretty fast, isn't it? Because now tau is something underneath t that produces 3,000 in the numerator. So it's 1 over 3,000. That's our tau, and we need 5 of those. 5 over 3,000. We're not having to wait very long before we get to our sinusoidal steady state, are we? 5 over 3,000. 1 over 600 seconds. And then we're there. We're in the sinusoidal steady state. Is that making sense? Yes. How did I get 1 over 3,000? I don't know. I'm asleep. But we have our h of s that gives us poles that contribute this e to the minus 3,000t with some sines, and you said these were 4,000 plus b sine 4,000. And this is just the transient piece, isn't it? I haven't included the sinusoidal steady state. The sinusoidal steady state is produced from this guy, the x. But now this 1 over 3,000 is all because of this guy. If you think of this as e to the minus t over tau, you are trying to find a tau such that 1 over tau is equal to 3,000, or tau is equal to 1 over 3,000. So this association between those two says that, oh, 1 over tau is equal to this 3,000, or tau is equal to 1 over 3,000, and for my settling time for the transient to be gone, after 5 tau, then I have the transient is gone in 5 over 3,000 seconds, or that's 1 over 600 seconds. 1/600th of a second, and I'm into the sinusoidal steady state. Is that making sense? I've started this, shaking this system with this x of t, and maybe what I should have, well, it doesn't really matter because I'm wanting the sinusoidal steady state. I could start this anytime. I could have hit it with a unit step to switch it on at 0. I could have said it's been shaking for infinity time. But I now want to know what's my sinusoidal steady state output after the transients, and the transients are gone in 1/600th of a second. Did that help answer your question where the 1 over 3,000 came from? What's my sinusoidal steady state? It's not that hard because we've already found all that we need to write it down. What's our frequency that we're interested in? If I'm shaking this system at 2,000 radians per second, that's what's going to be persisting in the output. So if you don't do anything else on the exam, you could at least say that. And you could say, well, I don't know what that is, and I don't quite know what that is. But it's going to be something like that. It's got to be, it's a linear system. You gave me an h of s, which is coming from a linear system, so I know that the output is shaking exactly at the same frequency as the input. But what is the amplitude of that sinusoidal steady state output? It's, pardon? And that's the original output of 2 of the input times how that input gets scaled as it passes through the system at that frequency, and we determined that to be 0.223. So the system reduces your input amplitude by a factor of 22% as it passes through at a frequency of 2,000 radians per second. So that's 2 times 0.223 is your amplitude. We clear on that? These can be very quick and fill-in-the-blank type of questions on exam 3 and the final. But you have to sort of know what you're looking for. What's the angle? So I now need to combine the original angle of -10 with the contribution of the system. The system is delaying the signal a little bit. That's what that means with the negative angle. We now have a minus 17.94 degrees. So there's a little bit of a phase shift, a little bit of a lag between the input and the output in the sinusoidal steady state. The output is a little bit behind the input at that frequency, but they're almost aligned. They're just 8 degrees apart. Questions on that example? Is sinusoidal steady state clear given a transfer function? All right, we'll do one more. I didn't get as many bobbleheads up and down as I wanted. Find the sinusoidal steady state y given the following information. Suppose somebody says, I'm going to give you an input that's 2 times the cosine of 6t, and the system that that input is being applied to actually has a transfer function h of s of 30, s plus 1 over s plus 10. Do you already have a image of the complex S-plane with the pole zero pattern on top of it, just given this information? Are you starting to see that? Are you dreaming poles and zeros? Nightmares? At least you're dreaming, right? What do you have? If I now said draw the pole zero pattern for this system, can you do that? So now I just felt like I was a physician with stitches. I don't know why that came to my mind, but maybe it's laces on a football that I just had going up the imaginary axis. I don't know. Gosh. Still thinking about the pizza on the mall. Uh-oh. Somebody's hungry. What do I put on this S-plane plot? How many poles do I have? I just have the one for my system, don't I? And it's going to go over there where? At minus 10. I'm hoping I had... Do I have anything else on that pole zero diagram? I have a 0 at minus 1, don't I? Is this a stable system? Is it minimum phase? Do you remember what minimum phase means? Is it stable and are all of my zeros in the left half plane? That's a minimum phase system. Is it minimum phase? Yes. So we have a stable minimum phase system. Those are well-behaved systems. Those are nice systems. Now, if I'm evaluating for the sinusoidal steady state, I've been using triangles because I don't want an X, I don't want an O. I want some distinguishing geometric shape so that you know that that's not a pole or a zero. I've been using triangles. Where do I put the triangle for this problem? If I'm finding sinusoidal steady state. So you're doing more than just pinning the tail on the donkey at a birthday party, aren't you? Because you don't have to do this blindly. You don't put your triangle here, do you? Where are you going to put it? So is it going here? Somebody said 6. So it needs to be on the imaginary axis, doesn't it? And I think I put 6 marks up there. This is now J6. So that I have contributions due to this 0 and contributions due to the pole. And I also need to keep track of that transfer function is in pole zero form, so that 30 is one of the scaling factors that I have to include when I find the lengths of my zero and pole factor. But now I can simply say, oh, I need h of j6, and that's going to be this L sub z and L sub p. In the appropriate numerator and denominator, and an angle. This is now my angle of my zero. This is my angle of my pole. I have the sum of all of my zeros factors minus all of my poles, and I just have one of each. And this actually ends up being 15.65 at an angle of 49 degrees. Questions on that? And does that make sense? Is your zero angle bigger than your pole angle by inspection? It is, isn't it? Your zero angle is pretty big and your pole angle is under 45. So you would expect to have a positive angle, and your lengths now, your zero length is about 6. It's a little bit more than 6, and your pole length is bigger than 10. So you now have maybe 12 dividing into 6, so that's 1/2, and there's your 1/2 of 30, or 15. So you can sort of eyeball this numerical number crunching that you might perform on your calculator. And if you have that particular piece of information, you now know what the sinusoidal steady state output is. That's the magnitude of your input that you started with, 2, scaled by 15.65. Cosine, it's going to be shaking at exactly the same frequency that we put as an input frequency of 6, and then we simply adjust its phase by the phase of our system. Questions on that? And it's clear where the L's and the Z's and or the LZ and the LP and the theta P and theta Z come from, isn't it? Questions on graphical determination of transfer functions? Let's look at Bode plots. Bode plots are just an extension of that idea. And if you can't figure out what Bode plots are, simply walk along the imaginary axis for several points, and that's your Bode plot. Find your magnitude at certain frequencies and plot that versus frequency. Usually you're plotting it versus log of omega or log frequency, and plot your phase as a function of frequency. Those are your 2 Bode plots. We're going to derive or develop ways to sketch this more quickly overall than having to do this point-for-point magnitude and angle computation. Let's look at a system just to get us thinking about where we might create a Bode plot. But again, a Bode plot could be in your stereo. That could be your graphic equalizer. You now have this frequency response shape coming from your stereo. Here, let's say that we have an op-amp based circuit. Let's say here's R1, and that's going into the inverting terminal of an op-amp. And maybe we have that feeding some load, potentially maybe even a speaker. Here's now our V sub 0. And let's put something in the feedback path and make that something frequency dependent. And now we have a circuit. First of all, is this op-amp set up okay? By that I mean, is it going to be well behaved? And what am I asking? I'm really asking, does it have negative feedback? You are feeding the output back to the inverting terminal. We do have negative feedback. So this is going to have these ideal op-amp behaviors or characteristics as long as we don't saturate things. And it's pretty easy to derive the input-output relationship or the transfer function between the input voltage V sub I and the output voltage V sub 0. Especially if we simply think of this as some generic feedback impedance, Z sub f. If I want Z sub f, what represent, or what can how can I express Z sub f? That's just R2 in parallel with that capacitor, isn't it? And I'm doing it in the S-plane, so I now have R sub 2 in parallel with 1 over SC. And that's this R2 over SC, where I'm multiplying the two impedances. And then I add the two impedances, which if I put them all over a common denominator in the numerator and denominator and cancel that SC, I end up with R sub 2 and an S R sub 2C plus 1. That's now Z sub f. So I'm going to write my equations in terms of Z sub f, and I'm actually going to just write a KCL right there at that inverting node. So I now have a voltage V sub n, and I'm going to compare that to the input voltage and the output voltage to establish my current. Since this is an ideal op amp, I could say that I have this current and that current and that current all summing to equal 0. But the current going into the op amp is 0, and so I just have two currents summing to 0. The one going from V sub n towards the input is V sub n of S minus V sub I of S over R1. And the one going towards the output is V sub n of S minus V sub 0 of S all over, what did I call it? Z sub f equaling 0. But I have the non-inverting node grounded, which is at the same potential then as the inverting node. V sub n is effectively grounded. I can now get rid of that here in these expressions, and I now simply have a relationship that I want, which is this relationship between the output voltage and the input voltage. I now have V sub O of S over Z sub f is equal to minus V sub I of S over R1. Or if I divide both sides through by my input's Laplace transform, I have V sub 0 of S over V sub I of S, and if I multiply everything by Z sub f, I now have the following transfer function for that op-amp circuit. Or H of S, plugging in what Z sub f is and taking R1 upstairs, I now have minus R sub 2 over R1 over S R sub 2C plus 1. Does that particular transfer function make you feel warm and fuzzy? What is it? It's a low-pass filter, isn't it? And it's what order? First order. So this is simply a low-pass filter. And you can tell me quite a bit about that low-pass filter, but before we get into that, a low-pass filter has this kind of frequency response, doesn't it, in terms of its magnitude? It's going to assume, although my sketch may not indicate it, at the lowest frequency is where it's going to have its maximum value, isn't it? So this is its maximum value, and you may be asked that on your homework. But if it's a low-pass filter, it's going to be maximum at DC. So you have a maximum value of your transfer function at dc, which is just h of 0. Then you have something interesting happening right here, which I might have been calling a lot of times the break frequency. That's where the magnitude response breaks or has a change in its behavior. The textbook might call this the cutoff frequency of your filter. What is that? Well, before we get there, it's equivalent to the pole, isn't it, in the system? Where is our pole? If we simply set the denominator polynomial, which is first order, equal to 0 and solve for s, we'll find where that pole is located. And we've called this particular piece of that expression the time constant, tau. So this is now s is equal to minus 1 over r sub 2c, or minus 1 over tau. And that, in this particular system, is our cutoff frequency. And a lot of things happen at that. That's also called the half power point in this filter. Or our magnitude is down by a factor of 1 over the square root of 2. And we'll see if we can see why that's the case in just a minute. But before we do that, what's the DC gain of this low-pass filter? I guess if I keep track of the minus sign, that would have been, that minus sign is minus r sub 2 over r sub 1. That minus sign just means that our sinusoids are inverted. Now, at the cutoff frequency, what is our magnitude? In our Bode plot, we do straight line approximations, and it looks like it's the same, but theoretically, this curve is going to be down a certain amount at that cutoff frequency, and that's the 3 dB that it's down. Where does that come from? And that 3 dB in absolute terms is 1 over the square root of 2. So let's look at the gain of this circuit. Let's say h of j omega, when omega, let's say, is the cutoff frequency, which is this 1 over r sub 2c. It's located where the pole is. And now if you sort of envision the S-plane, if you had a pole at minus 1 over R2C and you walk up the imaginary axis to J 1 over R2C, you can see the distance is now this length by a square root of 2. So that square root of 2 factor is coming into play. But let's now evaluate this at that frequency. This was now h of j 1 over r sub 2c. But the magnitude is now r2 over r1. We had j omega, but now we're replacing omega with r sub 2c. But that was j or s r sub 2c, and we replaced s with j omega, and we replaced omega with the cutoff frequency. So that's the result, plus 1. Is it clear where that came from? And now we have all these RC's canceling. Or we now have R sub 2 over R1 over J plus 1. But what's the magnitude of 1 plus J? Real part squared plus imaginary part squared added up. And then take the square root. And each of those is 1. So at the cutoff frequency, the real part of our pole factor is equal to the imaginary part. And you can see that we're down from the DC gain by a factor of 1 over the square root of 2, which is this 0.707 value in absolute or in real numbers. What if we wanted to know what that was in dB? What does 1 over the square root of 2 look like in dB? And dB is just 20 log of the number. So this is now, what's the log of a ratio or log of a quotient? Do you remember your log rules? What if I took the log of A times B? What's that equal to? Log of A times B. That's log A plus log B, isn't it? So now if I have log of A divided by B, it's log A minus log of B. So that we now have 20 times the log of 1 minus the log of the square root of 2. But what's the log of 1? That's 0 minus the log, and 2 we can say is 2 raised to the 1/2. The reason I'm doing that is because the 1/2 can now come out front in front of our logarithm because of the properties of logs. So that I now have 20 times 1/2 log of 2. So I now have 10 times the log of 2. But what's the log of 2? You all have this memorized, correct? Yes? Pardon? What did I do with the negative? I don't know. It just disappeared. Thank you. I had my glasses off. I don't know what happened to the negative. The negative is right there. Didn't you see it? It was red right there all along with my correction ink of red right there. Yes, thank you. I shouldn't lose that negative because I'm down, aren't I? I'm below where I started with at the DC by this factor of 1 over the square root of 2. And this is approximately 0.3 log of 2. So that I now have minus 3 dB. I'm 3 dB down at the break frequency from my DC gain value. That's where if people start talking about the 3 dB point, that's this critical frequency in a filter, which is usually then the break frequency or the cutoff frequency. That's where you start going into your stop band. Questions on that? Now, we have hopefully a little bit better understanding of when we start talking about cutoff frequency minus 3 dB point, this factor of 1 over the square root of 2. Let's examine now a Bode plot for a very basic transfer function, which is really what we just had, but I'm going to simplify it by saying we have a gain k, which was the R2 over R1, and I'm going to forget the negative sign that we had before. I'm just going to call it a gain k, and now I'm going to say that this is some time constant tau times s plus 1. Again, that's a low-pass filter, isn't it? And we know what the Bode plot should look like in terms of the magnitude response of that. It should be flat in our straight line approximation and then go down at what frequency? 1 over tau. And we know that at that frequency, in fact, we'll be down 3 dB, or this absolute value of 1 over the square root of 2. But let's now see if we can understand where some of these terms come from. We now have two terms in this transfer function. We have a gain term, which is just the k, and we have a linear term because it's just s plus, or tau s plus 1 raised to the first power, so I just have an s to the 1. We have a linear, and that's actually in the denominator, so I'm going to call that a linear pole factor, and I might even write that as tau s, and there's the 1 plus 1 to the minus 1. This is what gives us the fact that it's linear, and this minus 1 says it was in the denominator, it's a pole factor. Questions on those two terms? And if we can plot these two terms, we're a long way towards sketching Bode plots. And what we want to do is we want to look, a Bode plot is made up of two separate plots, a magnitude plot versus frequency and an angle plot versus frequency. We want to look at those two plots for each of these two terms. Let's now look at the magnitude and phase as a function of frequency. Really, we plot it with respect to log of omega. That allows us to get more frequencies on our paper, omega, for each term. Let's now look at the gain term. If I wanted the magnitude of the gain term, I'm now looking at 20 times the log, and this log that we're using is base 10. And now I simply find the magnitude of the absolute, or I take the absolute value of the gain, because I'll account for the minus sign in my phase. And this is, does k, it was not a function of frequency, was it? K is just a constant number. That might be 10, it might be 2. This is a fixed magnitude for all omega. And now what does that look like in terms of a sketch? That's just a flat horizontal line, isn't it? So if I wanted to have, let's say that this is my 0 dB line, that's supposed to be flat. And this is now usually log of omega, but I typically will just label it as omega. Now maybe if somebody gave me this and said, oh, your gain was 40 dB. What's that correspond to in terms of the absolute value of K? That's 100. So if you had a gain in your circuit of 100, you would have a contribution of 40 dB for all frequencies due to just that gain term. If I said, oh no, actually this system, oh boy, these are supposed to be flat lines. Man. 20 dB. That's a gain of 10. Because we're doing it in dB, we have a lot of range in our absolute value of gain that we can scrunch onto not as much vertical space. And the reason we're doing dB is because when we're doing logs, then we add numbers instead of worrying about multiplying. So we can look at each of these factors individually and add up their contributions since they're in dB and not have to worry that they were actually multiplied together in our transfer function. Since we're taking the log, now we just add up all of these individual contributions. In this example, we just have a gain term and a linear term, two terms that we have to add up. If somebody said, oh, you know what? That system had a gain of minus 20 dB due to the constant. Now your gain K is this 1/10 or 0.1. That's now the magnitude of our gain term, or the Bode plot, due to a constant. It's just a flat line. If you had a gain of 1, where would that line be? It would be right on that green straight horizontal line of 0 dB. A gain of 1 is 0 dB for all frequencies, because log of 1 is 0. Scale it by 20, it's still 0. What's the phase of this gain look like? So there's the first plot, the magnitude. Now we're looking at the phase of this constant K. You're going, well, it was a constant. But remember, it could have had a negative sign. So now it could either be 0 if K was non-negative, or it could be minus 180 if K is less than 0, and it's going to be this value, either 0 or minus 180 for all omega. And you could argue, why didn't you pick plus 180? I just like to have things in the negative because that represents a delay, which is typically what happens in most system responses, is you have a delay from input to output. But it could, a negative 1 could be a plus 180 in terms of degrees. But I'll just by convention call it minus 180. That means if you're sketching the phase plot of the angle of K, that's not that difficult to sketch either. Here is now log of omega, and let's say this is 0 degrees. You're either there or you are here at minus 180 degrees. This is if K is less than 0. You're here if K is greater than, actually greater than 0. If you have nothing, then you're no need to plot it. Questions on the constant term? Let's look at the linear factor. This is now tau s plus 1, which when we're marching up the imaginary axis, we replace s with j omega. And now we're looking at j omega tau plus 1. And now we get to do our fairy tales. Now we're in Goldilocks territory. Meaning, we look at small, big, and just right frequencies when analyzing these factors. Look at the magnitude of this linear factor. The magnitude in dB is 20 log base 10 of the magnitude of this complex number, which will be a function of frequency, isn't it? Omega. Let's now look at the extremes. Suppose we looked at values of omega tau that are much less than 1. So what does this really mean? This means that omega is much less than 1 over tau. And what was 1 over tau? That was our break frequency, wasn't it? And this much less, we're assuming that's a decade below. So much less than our break frequency. What does this magnitude look like when we're much less than the break frequency? If omega tau is much less than 1, how do I approximate j omega tau plus 1? I just forget the omega tau, don't I? I forget the imaginary part, and that just becomes 1 in terms of what's in the complex number. So this now for omega much less than 1 over tau. So this is omega much less than 1 over tau, and this was our pole location. And tau was our time constant. For this extreme case, when we have a frequency omega less than a decade below our break frequency, we can now say that j omega tau plus 1 can be approximated with 1. Or, therefore, this 20 log base 10 of j omega tau plus 1 becomes 20 log of 1, or 0 dB. So it's flat now. What if we look at, I kind of like taking those extremes. So that's the baby in Goldilocks story, right? That's the small, I don't even remember who's in this story. Oh yeah, it was 3 bears, wasn't it? It's been a while since I had to read fairy tales. Maybe I'll go home tonight and read one, fall asleep. So now what do we have? We have the little bear. Now let's look at Papa Bear, which means B. Suppose we take omega tau much bigger than 1. This now says that omega is much bigger than the pole, or the cutoff frequency omega sub c. So omega much larger than the break frequency or the cutoff frequency. And what do you think we're going to say that is? Well, let's say that's 10 omega c, and this other one, a decade below, was 0.1 omega c. So now if we're 10 times the break frequency, we can now say that j omega tau plus 1, how do we approximate that? Well, the imaginary part now dominates the real part. We now have j omega tau plus 1. We'll replace that with j omega tau. If we look at 20 times the log of j omega tau plus 1 in this operating range of frequencies, omega, we now have 20 times the log of j omega tau. But what's the magnitude of j? 1, isn't it? So this is now equal to 20 times the log of omega times tau, but tau was 1 over omega c. So this is now omega over omega c. And we know how to treat ratios inside a log. This is now 20 times the log of omega minus 20 times the log of omega c. And omega c is a fixed number, isn't it? Our break frequency. That's just a constant. So this is now a constant. And this is what we're plotting our Bode plot with respect to. This is our independent variable. This is now the equation of a straight line, isn't it? If you look at the left-hand side, that's y is equal to mx plus b. Something, and there's your 20 dB per decade. That's 20 times x. Your independent variable is log of omega. So this now says that if we look at this, suppose we said, well, what happens in this expression when omega is equal to omega c? Now we're at 0, aren't we? Which is where our original approximation was when we were at the baby bear location. So now we have intersected the two extremes right at the break frequency. So we were flat, then we were sloping, and they meet right in the middle at the break frequency. But this now, in terms of what we now have the magnitude is equal to 20x plus b. But because we were a pole factor, I didn't show it in that original expression, but we had that j omega tau plus 1 all raised to the minus 1. And that minus 1 would come out front and give us a slope of minus this 20x dB. So the pole factor says that we were in the basement, or the denominator. This pole factor was this j omega tau plus 1 raised to the minus 1. And so when we were looking at 20 times the log of j omega tau plus 1 raised to the minus 1, we now have this minus 20 log of j omega 1. Is that making sense? So in terms of the magnitude, we now have a way of creating, for a linear factor, a straight line approximation. A straight line approximation of the linear term for its magnitude if this is now our frequency axis, log of omega, and this is now the linear term, magnitude, in dB, where do we start at low frequencies? And let's say this is now 0 dB. And I'll just say here, let's say, is our cutoff frequency, omega sub c. We now know that below that, we were at 0 dB, weren't we? Above that, we were sloping because of the denominator factor of minus 20 dB per decade. And what we are doing is we're simply connecting those two straight line approximations, and we found that they intersected right at the cutoff frequency. And this is now our magnitude plot of a linear first order term in a Bode plot. It's flat until we hit the break frequency, and then we just go down at a slope of minus 20 dB per decade. What do we do for the phase? If we have this linear term, our linear term now is this j omega tau plus 1. If omega tau is much less than 1, this is the baby bear, isn't it? This is when omega is much less than 1 over tau, which is omega c. We said that that linear, or that complex number, looks like 1. What's the angle of 1? That's 0 degrees, isn't it? 1 is 1 at an angle of 0. What if we looked at, so that was A, at B, if we look at much bigger frequencies, see, they just want to come in and hear the bedtime story. Sorry. Omega now is much bigger than the cutoff frequency. And what did our linear term approximate to being? J omega tau. But what's J omega tau's angle? 90 degrees. And if it's downstairs, it's going to give you a minus 90 degrees. And now we just need to connect those. So a decade before, we're at 0. A decade above, we're at 90 or minus 90 for a pull factor, and we just connect them with a straight line. So our phase plot will be as easy or as simple as for a denominator polynomial, we have our cutoff frequency, omega c. We go down a decade. We go up a decade. We are at 0 here. We are at minus 90 here. And we simply connect that with a straight line. And this should be at minus 45 degrees right at the cutoff frequency if that was sketched properly. So we'll pick up at that point on Tuesday.